Okay, a ball of mass 5 kilograms and radius 1.2 is initially at rest at the top of a ramp that's 2 meters high and makes an angle of 30 degrees as shown. It then proceeds to roll down the ramp. When it reaches the bottom, some stuff happens. Oh, at the end they want you to calculate the moment of inertia of the ball?
Yeah.
Okay, no problem. So part A, calculate the initial and final potential energy of the ball.
That one, I got that one right.
Yeah, so the initial potential energy will be mg, oh man, mgh, and the final potential energy will also be mgh, but like, so I'm going to just set the height here is 0 at the bottom of the ramp. So
What did I do?
2 meters high. The ramp is 2 meters high. So that's 5 kilograms times 9.8 times 2. It's like 98 joules. You put newtons.
Oh, wait. Why is it in joules?
It's energy. Okay, and then final the final potential energy, the final height is 0, so the whole thing's 0. All good?
Yeah.
Part B.
I got that.
Calculate the initial and final linear kinetic energy of the ball.
So are none of these in fucking newtons?
Nope. Yeah, they're all in joules.
Okay, so I just took a fucking L on that.
So the initial kinetic energy would be equal to 1/2 mv initial squared, and the final kinetic energy would be equal to 1/2 of mv final squared. It says it starts at rest, so that's 0.
Boom.
So the initial kinetic energy is 0 joules. And the final kinetic energy is equal to 1/2 the mass of the ball, which is 5, times the speed of the ball at the bottom, they said was 5.4. So 5.
Oh my, what? Look at that.
You can square it.
Oh my god. I have it right there too.
Yeah. So 0.5 times 5 times 5.4 squared, 72.9 joules. Good sneeze, Sid. Okay, part C. Use conservation of energy to find the final rotational kinetic energy of the ball. So the initial energy of the ball would be the initial rotational energy plus the initial translational kinetic energy plus the initial gravitational potential energy.
So this is the one that was just.
And that'll equal the final rotational kinetic energy plus the final kinetic energy plus the final gravitational energy.
So when something's rolling like that, you always have to throw in a rotational?
Mm-hmm. Yeah.
Okay, so that's what I was like.
Yeah. Right, like if a record or something like that is just like spinning in place, and you put like and then you put a penny on it, wouldn't it do work on the penny?
Yeah.
Like the penny would move.
Penny didn't move,
right? So it must have energy, and it's not moving this way. It's moving on its own axis. So things that rotate have rotational kinetic energy. So the initial rotational kinetic energy is 0 because it hasn't. It's just like sitting at the top, right? And the initial kinetic energy is 0 because we said so. And the final gravitational energy is 0. And then we just like plug in all these other values that we had. So 98 joules is equal to the final rotational kinetic energy plus 72.9. That was really bad. Hold on. Undo, undo, undo.
Oh, there's an okay, sweet. So for this problem, that's what.
So then you literally just subtract. So 98 minus 72.9 is 25.1 joules.
If I would have got this problem right, I would have had this one right as well.
You subtracted?
Well, I would have ended up subtracting this number from that number.
Oh, it just didn't make sense to because you didn't.
Yeah.
Right. So 25.1 joules. And then part D, calculate the angular velocity of the ball when it reaches the bottom of the ramp. So the ball hits the bottom, and we're assuming that it doesn't slip. Yeah, it doesn't say it, but we're just going to assume that it doesn't slip. So we know the radius of the ball.
What do you mean by slip? What do you mean by that?
What do I mean by slip? I mean like a bowling ball.
Like slide almost?
Yeah, like where the ball like slides on the surface without rolling.
In this case, we're not saying it slides.
Right. So because V is equal to R omega, which is this is the equation I should have used
on the other one.
Yeah, on the other one. So the speed.
That's angular velocity. I have it on the formulation that you wrote for me.
Right. It's 5.4 meters per second. The radius of the ball is 0.12 meters. So you can figure out the angular velocity.
This guy decides.
It's 45. Radians per second. It's a lot, actually. .45 radians a second. Okay, then.
Now we calculate the moment of inertia.
Right, and the moment of inertia, because we know the rotational kinetic energy. Ow! Ow! So you can't use that 2/5 mr squared thing because, I don't know, maybe the ball's not solid. That equation only works for a solid ball.
Oh, so I'm not supposed to use this one?
No, in this case you'd want to use this one. I omega squared.
Right.
And so we know the rotational kinetic energy was 25.1. Trying to solve for the I.
See, I looked at this one on the test. You give it to us.
Yeah.
So I would not
use that one.
Gotcha.
Because this would assume that the ball. This would assume that the sphere is solid, that the ball's solid. You
don't know that.
You don't know that, right? Like. But you do know that for a fact that the rotational kinetic energy is 25.1. You know for a fact that the. What the hell? You know for a fact that the angular velocity is 45, so you can just solve for the I.
So wait, hold on. How do we know that the ball was, you said 25?
So that's 0.0248, and then I think the unit is like kilograms times meters squared.
See, this right here, getting this kinetic energy in front, how do you know to do that?
Well, this is just that's the equation for rotational kinetic energy.
Because okay, gotcha.
So this problem kind of worked it all backwards, right? Like you figured out what the translational energy was for both potential and kinetic.
Right.
And then you're like, well, those two things were supposed to equal each other because conservation of energy.
Right.
Why didn't they? Oh yeah, because it was also spinning. So that extra energy was picked up by spinning energy. Okay, and so because I know how much spinning energy it had and how fast it was spinning, I can figure out what the moment of inertia.
And that moment of inertia